So as a quick review of what we've discussed last week regarding liquid-liquid extraction, so we have discussed regarding this particular unique triangular equilibrium diagram for our three-component system associated with liquid-liquid extraction. This particular diagram is actually taken from this table. You have two sets of columns in this table. So in the first set, you will only use the MIK and the acetone concentration, which will be plotted in here. So this is for the acetone and this is for the MIK, short for methyl isobutyl ketone. As for the second set of column here, wherein you have the concentration of the acetone in the water phase and in your solvent phase, which is your MIK phase. So these two columns will be utilized in plotting this curve here. The equilibrium curve, horizontal is the raffinate composition. So your composition in the water layer, and the vertical axis is your composition of A in the solvent layer or in the ether layer. Okay. We also discussed the corresponding phases that are produced when we do extraction. So we can have a one-phase part of the system, and we can have the two-phase part of the system. So depending on the miscibility or the affiniation of your solvent to your feed or to the components of the feed. Now, this is our equilibrium diagram, triangular equilibrium diagram for our three-component system, and we're going to get its composition based on the location of the point that is plotted on the same diagram. And for equilibrium relationships, so we know that for each of the phases, so whether it's the raffinate phase or the feed phase, which is represented by X, or whether it is the extract phase, which is represented as Y in terms of composition, the sum of the concentration of each of the components has to be equal to 1. Okay, and then we've discussed the solvent properties. We discussed terms associated with liquid-liquid extraction and some of the many applications of liquid-liquid extraction. So for today, we will continue with the sample problem that will be using material balance. May it be overall material balance and component balance for our systems in liquid-liquid extraction. So we will start off with the second sample problem. Very simple illustration of how we use material balance in determining the amounts of the V and the L phase. So the V phase class is referred to as the extract phase. The L phase is referred to as the raffinate phase. So they are the product phases when we contact the feed with the solvent in the process of liquid-liquid extraction. So our raffinate phase is otherwise known as the water-rich phase, and our extract phase is otherwise known as the solvent-rich phase. So later on, you will be knowing regarding what is the continuous phase and what is the dispersed phase. We will just go to that when we are already in that part of the discussion. But nonetheless, your product phases, so you have two product phases in liquid-liquid extraction. You have the V for the extract and you have the L for the raffinate. Composition of the extract is Y. Composition of the raffinate is X. Composition of the feed is also X. Composition of the solvent is represented as Y. Composition of the bulk phase, which constitute already the phases that have been contacted, that is the feed and the solvent, its composition is represented as X as well, but it has only an added letter M on the subscript to denote that that's the concentration of the bulk phase M. Okay, so for you to understand the representation of the different compositions here. Now, we have been used to dealing with compositions in terms of mole fraction. Now, in the case of liquid-liquid extraction, it would be now mass percent or mass fraction that we will be using in terms of concentration. Now, let me just find my pen. Okay. Now, in this problem, you have already the composition of the extract layer given from the first sample problem that we have solved. So in here, you're given the composition of the extract layer in terms of A, B, and C. So review: A is solute, B is water, and C is your solvent. And the same thing, your raffinate layer composition was also given as 0.12 for A, 0.86 for B, and 0.02 for C, all in mass composition. The original mixture has the composition in terms of A, which is 0.10, and its amount is 100 kilograms. So you are required to determine the amounts of B and L. Okay, so please take a screenshot, okay, of the problem. That way, when we do our solution in the Jamboard, we won't go back to this slide in the topic of liquid-liquid extraction. So I'll go now to our Jamboard. Okay, wait, class. I don't see the Jamboard. Okay, we'll just share again. Okay, so I hope you could see now the Jamboard. So the given are actually explicitly stated in the problem because they are actually answers that we got by trial and error positioning of the tie line from sample problem number 1. So for the extract layer, so we'll have it as V. So this is the composition of the extract layer. So actually, we just need the A and the C, but if you intend to write the B, that's okay. So you have 4% for A and you have 0.94 for C. The reason why you just have to take note of the A and C of the composition of a particular phase in terms of A and C, it's because it's the only thing that you're going to plot. You're not plotting the composition of water. Now, in terms of the raffinate, so that would be our L. So a raffinate has an XA composition of 0.12 and an XC of 0.02. So this is 1. And then another thing, you're given the original mixture, so the feed, which is actually your LO in terms of the representation of Jean Coupley's. Extract is V1, raffinate is L1, so that's how it is. So your original feed is at 100 kilogram. And the composition of that, which is XAO, in terms of A, is 0.10. Now, in this case, the original mixture contained is 100 kilogram and the concentration was labeled also as XAM because in the first sample problem, I think we have contacted, let's see, I'll go back to our slide, because this one is a continuation of our first problem, sample problem. So let me go back to sample problem number 1. So you have an original mixture of 200 kilograms and it contains the following composition. It was equilibrated in a mixer settler. Okay, so I have changed in the case of sample problem number 2, I have changed the composition. So in that case, I have labeled it only as the original mixture is only 100 kilograms and that your XAM is equal to 0.10. Now, this XAM is your XAO because that's the original mixture that will be separated into 2 phases, the extract and the raffinate phases after they have been equilibrated in the mixer settler. if this is to be a continuation of sample problem number 1. So this XAM is also your XAO in that sense. Okay, so we'll go back to our Jamboard. So your XAO is equal to 0.10. This is also equal to your XAM. Why? Because we have only a single phase that was processed, mixed, and then allowed to come to equilibrium, and then the two product phases separated after they have already formed the two immiscible layers, the extract, the V1, and the raffinate layer. In this case, in this particular sample problem, you are asked to determine the amounts. So you are after the amounts of the extract and the raffinate layer. Okay, so V1 and L1. Okay, so we go to the solution.
Miss, ano siya ganyan, isang component B. Why na siya hidala?
B is water.
Okay, sige, Miss.
So we don't write the B. We don't write the B. Although if you intend to write the B, okay lang man siya, Bobby. Pero wala siya ga participate sa pag-plot. Kay A and C lang man ang gina-consider ta mag-plot. And another thing is, ang B, normally, once we know the A and C, gina-subtract naman lang sa sum sang duha from the 1. And then that's we know the B. When we do material balance, you can't find a book that does it based on water. So it's always in terms of the solute, the A, or either in terms of the solvent, which is the C. So wala ko na siya ginabuta ang B. But if you intend to write it, okay lang man. Okay? So we go back to the given. So this is our given, and we are asked to find the V1 and the L1. So if you do our material balance, you do overall material balance, your V1 and your L1, which is equal actually to your feed, is given already at 100. So I changed the given already to 100. Okay, so you have it there. So from here, your V1 or either your L1 could be expressed in terms of another. So you will have 100 minus L1. Okay, so this would be our equation 1. See, if you do component balance, it could be based on A or it could be based on C. I always suggest that you start with A. If you still need another one, then you can have another one in terms of C. And then it's patterned after what you have in here. So you have V1 YA1 plus L1 XA1 equal to this 100 times the composition of A in the original mixture, which is 0.10. That's our XAM. So let me go back. Okay, that's our XAM or XAO. And we started with 100. So I changed the given originally in the problem, which is 200. Then you will have to substitute the values that you were given in the problem. So in this case, we have 100 minus L1 for V1. Your YA1 is this one, 0.04. Your L1 is L1. We do not know that. And you'll have XA1. XA1 is this 0.12. All given in the problem. And this one is 10. And you'll be able to find L1. Once you have L1, you can get V1. So in here, in your component balance, you can also use solvent balance. So component balance on C, pwede man. So this would be YC1 and this would be XC1. So what's the value of L1? In our reference book by John Kuplis, he also used their inverse lever arm rule. But I said you can go straight to material balance and component balance. So your L1 in this case, can you give us L1? Or whoever got L1 already can just type on the chat box or so L1 is 75. Sige. Thank you. So 75 kilograms. Then it follows that your V1 is 25 kilograms. So that's how just easy it is. If you just simply do material balance overall and component balance. Okay, you may refer to the inverse Reveron application for this sample problem also in our reference book. But I always suggest that you use na lang this one because this is easier. Okay, now any questions here? I think there's none because that's very simple, as in very simple. So we go to the next topic here on our slide after this particular sample problem. Now, this is our single stage liquid-liquid extraction. In the first sample problem class, we have the first two sample problems. We have just one single feed. We have mixed it thoroughly, and we have allowed the separation of the two immiscible layers, the extract and the raffinate layers. So your feed was not contacted with any solvent for that matter. It was simply equilibrated. Now, in this case now, in this part of the slide, you will have a separate feed phase. Now, Jan Cookies labels it as L sub O. Okay, I'll just annotate. So this is your feed. And your V2, since this is single extraction, single stage extraction is your solvent. That's your V2. Your L1 is your raffinate. And your V1 is your extract. So the representation of the four phases in Jean Couplets are as it appears on this slide. So LO for the feed, V sub 2 for the solvent, L1 for the raffinate, and extract is V1. So when you do material balance in this scenario now, wherein your feed was contacted with the solvent, you will have LO plus V2 is equal to L1 plus V1, which is also equal to your bulk phase M, constituting the sum of the phases. Living and of course first process inside your liquid-liquid extraction unit. Now when you do solute balance, you just copy it here in terms of what you have started off in your material balance, overall material balance. You copy the phases and then you just multiply each of the phases with the corresponding mass fraction. So you have here X for the L's and Y for the V, and then the corresponding number following the subscript representing the basis that was used in the solute balance. So you have A0, A2, A1, and here also A1. In the case of the L1, which is raffinate, and V1, which is extract. Your XAM is the mass fraction of A in the bulk phase M, or the mass percentage of A in the bulk phase M. Normally, class, when we do material balance and solute balance, we have overall material balance and only one solute balance equation. If we make another solute balance equation, it will not solve for whatever additional required information in the problem that is stated. So mainly, you're only going to choose from any of these two. So it's an or. Not that you do overall material balance, then you do solute balance based on A and C. So it's an or between these two. But we know already that this one should be followed, and you have YA, YB, and YC. The sum of which will be equal also to 0. Okay, so that's our very elementary material balance for liquid-liquid extraction. Now we proceed to the next slide. Now in here, so this is, for example, your single stage equilibrium extraction unit. In the equilibrium diagram class, when you do a graphical approach, so let me annotate, Grace. You're going to plot, so in later on in determining the number of stages towards the latter part of this set of slides, we plot the composition of the feed, and that's the LO right on the horizontal axis, which is the X. So if you're, let's say for example, the feed contains 40% of the solute, so you place it always on the horizontal axis. So your LO on your triangular diagram will always be on this axis, your x-axis. Now, your solvent, most of the time, is 100% pure. So meaning, in terms of the composition, in terms of Y, your YC is equal to 1.0. So oftentimes, so what you have in here is a scenario wherein your solvent is pure C. So it's right on the tip of this triangle. Remember, our V2 is our solvent, so it's right on the tip of this particular triangle. We connect these two lines, LO and V2, and somewhere on this line is your bulk phase M plotted. Now question, how do you plot your bulk phase M right on the LO and the V2 line, which you have, which is a product of joining points LO and V2 in this triangular diagram? You simply determine, if not given in the problem, the XAM, or the composition of the solute in the bulk phase M. And then from the horizontal axis, where that value of XAM is red, you go up and rest on, you end on the line joining LO and V2. The trial and error process, so remember our first sample problem is also trial and error. The trial and error process of determining the composition of the extract, remember extract is V1. And I have mentioned in our previous discussion that extract is always on the upper part of the phase envelope. So the composition of the extract and the composition of the raffinate, L1 in this case, which is this time found on the lower part of the phase envelope, is determined using trial and error. Now, what am I saying about trial and error? So let me say, I'll draw here a different another diagram here below. So in the case of acetic acid and isopropyl ether, this was shown to you last meeting. You have another diagram here below, and you have the equilibrium curve here. Okay. Now, I say it's trial and error because you first select, let's see, I'll use another color. You first select a particular point on the phase envelope. This is your phase envelope. I suggest that you always start at the bottom. So let's say I'll just go with the point here. Let's say L1. You try to place L1 there. It could be anywhere here below. So L1 is there. Then what you do, you go down until you reach the equilibrium curve. You turn left until you reach the 45-degree line, and you go up until you rest on this particular point. So that's V1, okay? So now you have a point which started at L1, a point of your choice on the lower part of the phase envelope, and ended on V1 on the upper part of the phase envelope. Remember that you have initially already plotted M here based on the XAM, which you have projected on this line LO and V2. So what you're going to do is connect this V1 and L1. If they will pass through this bulk phase M, point M on the LO V2 line, then this is then the tie line. The tie line which will tell you the resulting equilibrated layers, extract and raffinate layers V1 and L1 respectively. So it's also a try and error thing Because, for example, if you choose a particular point here and you go down and you turn left and you go up, if you connect the corresponding point in here, for example, and that point in here, it doesn't pass through M, then that's not the corresponding tie line for this particular bulk phase M, resulting from the contact of your feed LO and with your solvent V sub 2. Okay? I'm just explaining it initially in here, but later on when we do graphical approach at the latter part of the set of slides, in determining the number of stages, we will revisit again this particular concept. But nonetheless, I want this fundamental thing already very clear to you. You always connect the feed and the solvent points in your equilibrium diagram. On this particular line connected by these 2 points, you have the bulk phase M taken from the projected concentration XAM to this particular line LOV2. Then the tie line is determined trial and error as long as the points that you will have placed in the phased envelope referring to the L1 and the V2 when connected is passing through the bulk phase M. Okay, so then this is one stage. The way we count for the number of stages, graphical, for liquid-liquid extraction is in the number of tie lines that we are producing. So in this case, since we're talking about a single stage extraction problem, so this is your one tie line because you only have a single stage. Now, in terms of determining the concentration of V1 and L1, it's a simple case of read out. So, ang gwa, I'll just erase the marking. So, di samok ang gwa, you're just simply going to read the concentration here. For L1, you have your XA1 here. And you have your XC1 here because this is C. The same goes with the Y. So you have, in terms of V1, so you have YA1 here, and you have YC1 here. As for the B, you just add the two composition and subtract the sum from 1. That would be your B composition for the two product phases, the extract and the raffinate phases. So that's the graphical way of knowing it. But graphical approach is only done if possible. That is, if you're given the equilibrium triangular data or that set of triangle and rectangle here below. If not, then you have to resort to the use of the Krimser equation again, which we will be discussing, and the simple material balance equation discussed just a few minutes ago. Okay, so I clear my markings now. So we proceed to this part. There is a need for me to discuss this initially because the concept will be used in solving this particular sample problem. Sample problem number 3. A feed mixture weighing 200 kilograms of a known composition containing water, acetic acid, and isopropyl ether is contacted in a single stage with 280 kilograms of a mixture containing 40 weight percent acetic acid, 10 weight percent water, and 50 weight percent isopropyl ether. Now take note that in this case, your solvent, the 200 kilogram mixture solvent, is not pure isopropyl ether. It also has the 3 components present in the feed. The resulting raffinate layer in this case weighs 320 kilograms and contains 29.5 weight percent acetic acid, 66.5 weight percent water, and 4.0 weight percent isopropyl ether. You are asked to determine the original composition of the feed mixture, which is unknown, and the composition of the resulting extract layer. So we will now together get a picture of this particular slide. So in the discussion of the solution, you will have something to refer to without going back to this slide again. Okay? Please take a picture. And we'll go to the Jamboard for the solution of this. Okay, I'll go now to the Jamboard. Okay, this is sample problem number 3. So we'd like to write down the given for this sample problem. Okay. If we're going to simply draw a box for our extraction unit, so since this is single stage extraction, we can do so. And you will have here your LO or your feed, and that LO is 200 kilograms. It is contacted with this other phase, which is your solvent, which has a mass of 280 kilograms. So you just refer to the screenshot that you have taken. XA is 0.4 and XC is 0.5. So you also were given water, but I will not write it anymore. Now you were given that the raffinate layer or the water-rich layer has this as the mass, 320 kilograms, and this particular composition. So this should have the subscript 2. And by the way, this is Y, not X, okay? Now you have XA1 here, which is 0.295, and XC1, which is 0.04. Now this is your extract, which is V1. Okay, so far these are the information stated in the problem. You are to determine the composition of the feed. So then you are after XAO, XCO, XBO. Composition of the extract, YA1, YC1, and YB1. Okay? So any question as to our representation? Okay, I think there's none. So we go to the next slide for our solution. Now, if you do overall material balance, so you will have the feed plus the solvent should be equal to the raffinate and the extract layer. The feed is given to be 200. So I'll show to you this one. It's 200. You have 280 here and 320 for the extract and the raffinate layers respectively. Sorry, for the solvent. Sorry, this is your solvent and the raffinate layers. 280 and 320. So you have B2 here. It's a known. Sorry. Your solvent is 280. So this is 280. It's our extract, which is unknown. So your raffinate is 320. And you have extract V1 as the unknown. So your V1 is 160 kilograms. Now, from the figure, the triangular diagram with the rectangular diagram at the bottom of your acetic acid and isopropyl ether, you're going to read out the corresponding composition of the extract layer. So from equilibrium diagram. So how is that? So this is how you're going to solve it. Let me share this acetic acid triangular diagram. Share ko ulit. Okay, then I will click on this Problem has been solved. So I just want this diagram. Never mind the answer, because they're going to ask you for the answer for the payment. We just want this diagram here. But I can't. Wait, class. I look for a different site where we can have an enlarged diagram for this. Or I can have this screenshot is buried B. So this will appear bigger. Okay. So get it from here. Okay, we'll make it appear bigger. Okay. You can see the equilibrium diagram here for your acetic acid isopropyl water system. So that's our equilibrium diagram. Our goal is we will find the composition of the extract layer. Now, since we know already that your raffinate and extract layers are equilibrated in the process of extraction, then it would be a tie line. We would rely on the constructed tie line of this raffinate and extract layers extracted from our equilibrium diagram. So what do I mean by that? Since we are given already the composition of the raffinate layer, if you have your screenshot there with you, it says that it's 29.5% A. So where do we get that one? So in here on the horizontal axis, let's just annotate. On the horizontal axis, you look for 29.5A. So this is 0.10, 0.20, 0.30. So probably this one, this 0.295 is somewhere here. Not really on that line where you have the point, where you have the 0.3, but here, you see this dot here that I have written. So this is your actually L1. That's your L1. So what are you going to do with that? So just like the way we have done with the previous sample problems, you're going to look for that point which will be equilibrated with this L1, and that point is the V1. How do you find the V1? By the use of the tie line. How do we construct the tie line? We use the process that we have used in the first sample problem and in the third sample problem, or rather in the second sample problem. So what you're going to do is you go down. So you rest on the curve. You turn left. So that's your procedure. In here, you go down. In here, you turn left. So you have this point here. So let's say it just stopped in this particular vertical line. So you have this point now, right? You're going to connect. You have that. So then this must be the very important extract. Now remember, as per concept, that your extract and your raffinate layers are equilibrated. So we'll connect these two with what we call as the tie line. Palikuon ko lang class na. That's our tie line. This is the tie line. So upon the construction of the tie line, you'll be able to read the composition of the extract, which is YA1 and YC1. So in this case, it's resting on this line. But if you're really going to go use the equilibrium diagram on paper, not this one because this one is crude, you'll be able to get this corresponding concentration for your extract. So your V1 will have the following concentration. So you have YA1, which is more or less 0.125. So in this case, in approximate ko na lang dira. Pero actually, mga diri lang na siya ho. And then you will have your YC1, which is more or less equal to 0.870. Your YB1 then, taking the sum of these two and subtracting it from 1 will be 0.005. You need these compositions. That way you'll be able to know the composition of the feed, because the problem is asking for the composition of the extract layer, which is already this. This is already the composition of the extract layer. Now we're going to find the composition of the feed by simple component balance. Now, before we go back to our Jamboard, do you have any question as to the procedure that is being done here in finding the location of the extract layer? Okay, so none. So please take note of the corresponding composition of your extract layer from after we have done the construction of the tie line using this particular diagram. If you're not given this diagram, you'll be given a table similar to the one that was shown to you for this system, and you are the one who's going to construct the phase envelope here and the equilibrium curve at the bottom. Okay? So I will clear my markings here and we'll go back to our Jamboard. Okay, can't find my Jamboard anymore. Okay, wait, class. So on our equilibrium diagram, we will write now the corresponding composition of the extract layer for V1. So you have YA1, YC1, and YB1. So these are the compositions that were written then in the equilibrium diagram for our system. So using the A and the C component balance, you can find the composition of the feed. Oh, I cannot make any more frames. So wait, class, ha? It says here, I cannot anymore make any frames. So we'll just delete this one. Okay. So we do component balance on A. After that, we do component balance on A. So our LO, our feed is 200. We do not know its A composition. We add to it our solvent, which is 280. We multiply it with the A present in the solvent. Now our extract, which we computed to be 160, its A is 0.125 based on the figure. And our raffinate is 320 with this given composition on A, which is 0.295. So from here, you'll be able to get the XA, which is equal to 0.012. You do also component balance on C. That way, you'll be able to find the composition of your feed in terms of C. So you have 280 times 0.5. This is the C in your solvent. You have 160 multiplied to 0.870. This is the YC1 that we got from the figure, and we have 320 for the raffinate multiplied to its C composition as given in the problem. So you have XC equal to 0.06. Your XB will just be 1 minus XA plus XC. So your XB here is equal to 0.928. Okay, so very simple. You cannot solve the problem purely analytically because you need to know the composition of the extract based on the construction of the tie line. From the raffinate given composition to the extract composition. And then once you have it, then you can go to the use, or resort to the use of the material balance. Okay, any question for this problem? Okay, none? Okay, so we'll continue on our slides. I'll go back to our slide. Okay. Okay, so we have determined the original composition of our feed in this case, and we have taken the composition of the resulting extract layer from the equilibrium diagram. Now we go to types of equipments and design for liquid extraction systems. So the first equipment here is the mixer settler type of equipment wherein you have a single feed, you have it equilibrated, you have mixed it, you homogenize the system, and then the system after homogenization goes to a separator. So it's referred to as a separator because this is where you have the separation of the two immiscible layers, the extract and the raffinate layer, after equilibrium. So that's how you separate the two. Now, your mixer settler could be also of this orientation or of this design wherein it's just one unit. You have here your mixing chamber, and after they have mixed and homogenized, you have this particular portion in your equipment where the two layers are allowed to come to equilibrium and separate from each other. But both are considered as the mixer settlers type of extraction. And of course, we have this one. This one, the colored one, is just this. Okay, I have taken this from the web to illustrate how the light phase and the heavy phase streams are equilibrated, mixed, homogenized in this part of your mixer settler. The heavy phase class is the feed. The light phase is the solvent. Okay, so other books use other terms referring to the phases that are contacted in extraction. So heavy phase is your feed, light phase is your solvent. They are mixed here, and once mixed, the mixed portion is now separated into two layers. So you have the heavy phase layer is your raffinate layer. They're separated now after equilibrium is reached, and you have the light phase layer here, which is your extract. Okay, but this is still your mixer settler type of equipment. Now we have spray type extraction towers, just like absorption towers and stripping towers, and we also have packed extraction towers. So in spray type extraction towers, we have the heavy liquid or the feed introduced at the top. So your heavy liquid goes down. As it goes down, it comes in contact with the light liquid that is dispersed through the spray nozzles. So the light liquid or your solvent is introduced at the bottom, and it flows counter current to the heavy liquid feed that goes down. Your extract is removed on top of the column or of your tower, and your raffinate is removed at the bottom. Okay, so this is your spray extraction tower. They are not often used, but some special occasions they are utilized. So this is also a spray extraction tower. So the liquid are sprayed downward, referring to the feed. You have here your solvent introduced at the bottom and flows counter current to your feed that goes down. Now, when are these particular types of towers used? So very special in the case of those systems which have, aside from the physical separation, which have the occurrence of rapid, irreversible chemical reactions, such as in the case of neutralization of waste acids. So it's not just a simple case of separation in this case, but you have to consider the chemical reaction already. Spray extraction towers are not as tall as pack extraction towers because they can only have as much as 1 or 2 stages. So oftentimes 1 stage only. It's low cost, but as in special application only, so it's rarely used. So we have the packed extraction towers, which is oftentimes used because it's more efficient than the spray tower. Now, used only when a few stages is needed, but more than that of the extraction or that of the spray tower, and with the interfacial tension just around 10 dyne per centimeter. So it should not go beyond 10 dyne per centimeter. But there are problems actually that can operate. You have a packed extraction tower which can operate on an interfacial tension of 25 dyne per centimeter. But it's still allowable. On the efficiency side, so supposed to be, it should be only around 10 dyne per centimeter. Excuse me. The choice of packing material here is based on the continuous phase. So here we go. The continuous phase is your heavy phase or your feed. Okay? Your continuous phase oftentimes is your heavy phase or your feed. Now, uses preferably random packing over structured packing material. So your pack extraction towers utilize random packing materials because random packing materials have more interfacial surface area exposed compared to structured packing. If you're using the concept of the HETP in gas absorption, then so you will have the height equivalent to 1 theoretical plate. In here, we use the term HETS for extraction. Height equivalent to a theoretical stage, HETS. Now, in the normal packed extraction tower, this HETS is greater in value or higher in value than mechanically agitated extraction towers. So we have even special types of towers which we're going to discuss later on. I think towards the end of this set of slides. Now, in the design of our extraction tower, so we have done, you were shown already on how to determine the amounts of the extract and the raffinate layers, how to determine the composition. Now we go to the design of your extraction tower. The basis of how big your extraction tower should be is on the flooding condition. When is the tower flooded? So you determine that particular condition when the tower is flooded, and then you're just simply going to lower down the corresponding flow rate. That way, it will not be flooded anymore. So what is in the first place this flooding condition? So this occurs when we increase either the flow rate of the dispersed or the continuous phase. So whether you increase the flow rate of the feed or whether you increase the flow rate of the solvent, when increasing such flow rate will make both of the phases, so meaning both of them, the feed and the solvent phases, leave the continuous phase outlet, then we say that your tower is already flooded. So in our language, kung pataasan mo ang flow rates ang solvent or pataasan mo man ang imong nga feed flow rate, nga duha gid sila manaog sa continuous phase outlet, dito siya manaog sa dalom, sa raffinate phase nga outlet, then your column is said to be flooded. So it is recommended that you know this condition, or you first determine when is the tower flooded, and based on that particular condition, when it is flooded, you decrease the flow rate by 50% of the flooding condition. Some problems would even resort to increasing this to 60%. But if the problem is silent as to what would be the basis of your design, then use the 50% of the flow rates at flooding. So determine when your column is flooded, and then the flow rates you decrease by half its value. That way the column won't be flooded anymore. Okay? Now, there are diagrams that you can use, or you should, by the way, you should be using this diagram in determining the condition at flooding. So we have this flooding correlation diagram for packed extraction tower. So we can attribute this to Crawford, Wilkie, and Wilkie. I think your handbook has this equivalent flooding correlation diagram also. So in here, normally what we determine is the ordinate, the y. So we're so used to determining the x and then determine the y. In this case, we determine the y, the ordinate. Then once we have that value, we look for it in here and project it on the curve. Then end on the curve and read out the corresponding abscissa value here. Okay, so determine this first and then determine the abscissa value. Now, in determining the value for the ordinate, you have parameters here that you need to determine for your system. Most of the time, the problem gives this one. The densities, the sigma, that is the interfacial tension, even the viscosity are given in the problem. So you're only going to determine the void fraction and the surface area A from a table. Okay, and then you just substitute everything on this formula so that you'll have already the ordinate. Once you have the ordinate, read it out here. You can have the abscissa. From the abscissa, you'll be able to solve for the very important flow rates, the volumetric flow rate of the continuous and dispersed phases. Take note, at flooding. So meaning flooded siya sa sininga mga values mga solve. So once you have already the flooded values, you decrease it by half. And that should be the basis of determining the diameter of your extraction tower. So speaking of the ordinate here, which will be needing the A and the E, which is based on your packing material, I think this is the table. So this is the table we're going to find the value of the A, the surface area of your packing material per unit volume of the packing material used. So you have here on the first column, the type of packing material, and you have here the A, which you need in that particular formula for the ordinate, together with the void fraction, the epsilon. So you're going to get the values here based on the packing material used. What goes with this particular table is the table where you're going to get the HETS. In this particular table, you have here the type of extraction tower, the capacity of the combined stream. So this capacity of the combined stream is the decreased capacity already. So you have the flooding capacity. You decrease it by half. So the sum of the halves of the VC and the VD will be the one that is written here on the range. So for packed towers, it should be within this range of 12 to 30 cubic meter per square meter per hour. For spray towers, you have 15 to 75, and so on and so forth. So this is the combined capacity, not at flooding, but 50% of the flooding. And for a particular type of tower, you have here the height of equilibrium stage. So the range of the height of the equilibrium stage. So what then would be the proper HETS, or what's the actual HETS that you're going to substitute to a particular problem? It should be the average of the value in the range. So for example, for a packed tower, your average HETS will be 0.4 plus 1.5 divided by 2. So that's 1.9 divided by 2. So that would be the HETS for a packed tower. So for a structured packing tower, you have this one. This is structured. So this one is already for random pack tower. Sieve tray, pulse pack, pulse sieve trays, and Chibel tower. You also have the car towers. You'll know these towers later on at the latter part of the slide. Okay, so you need the HETS here. So if we design our column, extraction column, we need to know how big it is. So that has something to do with its diameter, and we need to know how tall it is based on the HETS and the number of stages that either we determine, the theoretical number of stages, or the problem gives us. Okay? So 1, 2, 3. You need these 3 when you solve for, or when you design your extraction tower. Okay. So this would be our sample problem in this case in the use of those tables and diagrams. So toluene as the dispersed phase is being used to extract diethylamine from a dilute water solution. So your diethylamine is mixed with water solution. Toluene, your organic solvent, is the dispersed phase, and your diethylamine in water is your continuous phase. Your packing tower uses 1-inch pall rings and is at a temperature of 26.7 degrees Celsius. The flow rate of toluene V, so notice it's V because we represent the solvent to be V, is 84 cubic feet per hour. And that of the water solution, referring to our feed, is 56 cubic feet per hour. The physical properties of the dilute solutions are, so for your aqueous continuous phase, and that's your feed, its density is 62.2, nearly same that of water. Its viscosity is 2.080 pound-mass per hour per foot. And for your dispersed phase, which is your solvent, you have its density as 54 pound-mass per cubic feet. The interfacial tension is 25 dyne per centimeter. So predict the flooding velocity. Using 50% of the flooding velocity, determine the tower diameter. If the separation requires 5 theoretical stages, calculate the tower height. And D, compare your results when you switch the two phases. So meaning your aqueous phase will be dispersed, meaning your toluene will be introduced at the bottom of the tower, and your continuous phase is your toluene, which is going to be introduced at the top of your tower. So lion sila nga duwa. Which one will require a bigger or a taller tower? D will be your assignment that will be submitted when we meet on Thursday. Okay, in our class on Thursday before the quiz. As for its canvas, I will just put it up later after the class where you're going to have it submitted on canvas. But its hard copy will be submitted on Thursday. Okay, we'll do now the solution of this problem from A to C. Okay, so please take a picture of the problem. That way, it's we get to solve it faster without having to go back to this set of slides again. Okay, somebody wrote in the inbox. Ni sa Canvas sa Tuesday ang deadline. Oh, sige. Sa Tuesday, sige, Nika. We'll have it on Tuesday then. Kaya may quiz gali ka mo sa Thursday. Gin-move ko siguro. So we'll have it on Tuesday next week then. Both for the hard copy and the, of course, in Canvas. Okay. Have you taken already a screenshot of the problem? Please take a screenshot and we'll have it solved on the Jamboard. Okay. Sige, I'll transfer now to the Jamboard. Okay, we'll go to the next vacant slide. So we'll have this cleared, class. I cannot make any more because I have plenty of Jamboards, I think. So that is why they're not, Google is already limiting my use of additional files. Okay, that's it for now. Okay. Given. So this is our tower. So toluene as the dispersed phase is being used to extract diethylamine. So then this must be our B sub D. So toluene as the dispersed phase. Based on our illustration, by the way, I was not able to give an illustration. So this is our illustration for an extraction tower using the orientation of the dispersed and the continuous phases. So the dispersed phase is introduced at the bottom, and I was not able to show to you the schematic. So this is our schematic diagram. In our problem, in this case, this is toluene, and this is 84 cubic feet per hour. Our continuous phase or our heavy phase, our feed, is introduced on top, and its flow rate is 56 cubic feet per hour. Your tower uses 1-inch pile rings. So it's a pack tower, and it's operated at 26.7 degrees Celsius. Okay, and then of course, this one will be your, in our representation, this is our extract. So I will just represent this is E, and this is our raffinate. Because this time we're not using the representation LO, V2, V1, and L1. So your extract lives at the top, your raffinate lives at the bottom. The other required information in the problem are as follows. So for your continuous phase, you have the density, you have the viscosity, okay, the feet squared is a continuation of or rather it's just the feet. Pound mass per hour, feet per foot. Then we have for the dispersed phase, we have the density here to be 54. Now, the problem gives us the interfacial tension. So this is what I mentioned, that the interfacial tension, even if it's just limited to 10 dyne per centimeter, in the case of pack tower, this problem has 25 dyne per centimeter for its interfacial tension. Okay, I think that's it in terms of the given for this problem. Required. So letter A, flooding velocities. So we'll have the BC and the BD here at flooding. Letter B, at 50% flooding, you are to determine the tower diameter. Letter C, for n theoretical equal to 5 stages, what's the tower height? Z. Okay. Okay, that's our problem. These are the required information. This is our given information. Okay, now we'll go to the solution. So I mentioned a while ago that the solution always starts with determining the ordinate of our flooding diagram. So let's go to our flooding diagram and write down the corresponding ordinate. So what is that ordinate? So I'll go to our slide. So you need to determine this. The sigma over rho c raised to 0.2, the mu c over delta rho, the A over epsilon raised to 1.5. Okay, so please take a screenshot of this formula so we can go back to our Jamboard. Okay, go to our Jamboard. Solving for the coordinate of the flooding correlation diagram. So I will just write the equation on the next slide. So your ordinate equation is sigma divided by rho c. This is raised to 0.2. Then you have mu c divided by delta rho. This delta rho class, by the way, is the absolute difference of the two densities. Then you have here A over epsilon raised to 1.5. So if we're going to answer this one, so for our sigma, it's 25 dyne per centimeter. Now, this is a problem that works on English units. So your dyne per centimeter is SI. So you need to convert it to a pound mass per hour squared. The conversion I have written also in the slide class in the next part of that slide, but I will just write it in here. So you're going to divide this 25 by 28,572. Okay, that's your conversion. Now your unit here is pound mass per hour squared. Okay, so that's for your sigma, yes, your sigma only. You have still the density of the continuous phase. The density of the continuous phase is 62.2, close to that of the value for water. So I'll place it in the denominator. This one's supposed to be is in here, in the numerator for the conversion only of sigma. So you have 0.2. For the mu c, that's the viscosity. The viscosity of the continuous phase is 2.080. I'm not sure if it's written here. It's here, pound mass per hour per foot. Okay. So that's that one. We divide it by the difference of the densities. So you have 62.2 minus 54. Okay, densities. And then I'll just write here the A. So where are you going to get the A and the epsilon? So you're going to go back to our slide and get the A and the epsilon based on the packing material that was used. Okay, because okay, so based on the packing material that was used, you have this. For 1-inch pal rings, 1-inch pal rings, you have here the void fraction, which is 0.94. That's your epsilon. And your surface area per unit volume of packing material in English, because we're working on English units, is 63. So A is 63, epsilon is 0.94. Okay, so we go back to our slide for that, to our Jamboard. Okay, so we have here A, which is 63, and an epsilon, which is 0.94. So you'll have here an exponent of 1.5. So for this ordinate, I'll just use the value that is given by John Couplis. You'll have 902.8 for the ordinate. Now, what are you going to do with that 902.8? We'll go back to our slide. And look for the flooding correlation diagram. This one. So your 902.8. So this is 200, this is 100. So this is 200, 300, 400, 500, 600, 700, 800, 900. This is the 900 here. 902. So a little bit above that one. So I'll just put here a mark that is a little bit higher than the 900. So more or less this one. That's that one. Okay. Based on the ordinate that we have solved. Then we read out here your abscissa, the value of this group of variables and parameters. So this one is more or less 170. This is more or less 170. This is 100. This is 150. This is 200. So 170. Okay. So I'll clear my markings here. And we go back to our Jamboard. So you'll get from diagram abscissa is more or less 170. Now, this 170, you will equate to the equation for the abscissa. So, you'll have 170. You will equate it to V sub C raised to 0.5 plus V sub D raised to 0.5. The sum of this, you square and you multiply to rho C, and you divide everything by the product of A and mu C. Okay? Now, in here, you have VC raised to 0.5 plus VD raised to 0.5. Okay, that one. We'll keep it there on that side. So that's squared, and then we'll cross multiply everything. So you will have 170. Your A is 63. Your mu C is 2.080. We have it already. So cross multiply sila sa 170. And then we divide by density of the continuous phase, which is 62.2. If you get the square root of both sides, you will have V sub C raised to 0.5 plus V sub D raised to 0.5 equal to, so taking the square root of both sides, you will have here 18.92. So this is your first equation. The ratio of the V sub C to V sub D in the problem is equivalent to the volumetric flow rates of the continuous and the dispersed phases. So for the continuous phase, okay, your continuous phase is 56 cubic feet per hour, and your dispersed phase is 84. So 56 over 84. Now from this one, you'll be able to get a VC over VD equal to, so 0.667, or VC is equal to 0.667 VD. If you substitute 2 to 1, you'll be able to find both the V sub C and the V sub D. So substitute 2 to 1. Your V sub C is equal to 72.3 feet per hour, and your V sub D is 108.45 feet per hour. These are the linear velocities of the continuous and dispersed phases. This is at flooding, meaning at these linear velocities, your column is flooded. So this is already the answer for letter A, the flooding velocities. So for letter B, you're going to use only 50% of these values. So at 50% of flooding conditions, your VC and VD will have these two values. So your VC is 36.15 feet per hour, and your VD is 54.2. This is feet per hour. Okay? Now, if you're going to get the sum of these two, VC plus VD, the sum is 90.35 feet per hour. Why do you need to get the sum of these two at 50% of the flooding? You need to check from the third table. So take note of the value, 90.35 feet per hour. If you're going to have this converted in meters, you need to divide this by 3.28. This is equivalent to 27.54 meters per hour. So the reason why there's a need for us to convert here, it's because in the table, you have the range of the sum of the velocities of the continuous and dispersed phases in meter per hour. So we'll check. So our value is 27.5. We'll go back to our slide. This is the table I'm referring to. So for packed towers, this is your packed tower. The range of value for your VD and VC, the combined capacity that your column will not be flooded, should be in the range of 12 to 30 meters per hour. So in this case, you have it in 12 to 30. Our answer is 27. So we are on that range. Now, since we are on this table already, since we have a packed tower, then we might as well get the HETS here for our letter C later on. The height equivalent to one theoretical stage. So 0.4 to 1.5. We need it later in determining how tall should our column should be. Okay, so okay pa kita. Kay 12 to 30 siya. So I'll click my markings, erase my markings, and then go back to the job board. So 27.5. So in the table, we have up to 30. Okay, so now our goal in letter B is to determine the diameter. Okay, the diameter of the column. And since we have already the linear velocity, take note, I'd like to emphasize this. In computing for the diameter of the column, you use the velocity or the flow rate. You use the velocity and the flow rate of the continuous phase, not the dispersed phase, but the continuous phase. So in determining the area of our tower, that should be the volumetric flow rate of the continuous phase divided by the 50% of the flooding velocity for this particular phase also. So our continuous phase is flowing at 56 cubic feet per hour. We divide it by the linear velocity at 50% flooding. Now that linear velocity is only 50% of flooding, 36.15 feet per hour. So in here, you'll be able to solve for the cross-sectional area of your tower. From in here, you'll be able to find the diameter. So pi d squared divided by 4 is equal to 1.549. And your diameter here is 1.404 feet. This is in feet squared. So that's the diameter of your extraction tower. Next would be the height. So I'll place here C. We need to get the average of the range of values of HETS from the table. So a while ago, I encircled 0.4 to 1.5. So you have 0.4 plus 1.5 divided by 2. That should give you 0.95. So 0.95 meters or equivalent to, so that's in meters, 3.117 feet. So just like in gas absorption, in determining the Z, you have the number of theoretical stages, this time times HETS, not HETP. So the problem gave us 5 theoretical number of stages and we multiply it to 3.117 feet. Now, if you multiply this 3.117 and 5, you'll have 15.585. But you don't answer this raw data class because in extraction tower, you need to have allowances for the settling zones and for the inlet nozzles. So for your inlet nozzles, you have to give 2 feet for the allowance. For the settling zones, another 2 feet. And then this one based on the theoretical number of stages. So plus 15.585 feet. So the true tower height then is 19.585 feet. So don't forget to add 4 feet for the settling zones at the bottom, or the settling zone at the bottom, and the nozzles that you need, the feeding nozzles, inlet nozzles at the top. So that would be your tower height. Now you learn something new here when you do the problem wherein you switch the continuous phase and the dispersed phases. You can compare how big your column should be and how tall should it be if you interchange the two phases. Any questions here for this problem?
None, Miss.
Okay. Sige. So on Thursday, okay, I'll stop sharing here if there are no more questions.